So thank you very much. I hope those of you coming in finding a seat. So in this talk, I will give a quick history of computer mathematics and touch on how it came to influence the development of actually several programming languages. Most notably early functional programming languages like ML, which we heard a little bit about in today's keynote by Don Syme. It is also, in part, a history of AI, by no means complete. So today, AI has become almost synonymous with machine learning and neural networks. I won't talk about that, so if anyone was interested in that, I'm sorry to disappoint. However, I consider that AI actually consists of more than just learning. Another important part is reasoning logically, rationally. And especially in the domain of mathematics, reasoning and learning together is what is needed to make something powerful and useful. So in addition to reasoning and learning, another factor which I think is quite interesting and important to get into our future smart computer systems, to call them smart, is actually creativity. So I will also talk, after this little bit of history, I will talk a little bit about my current research in how we can get computers to act creatively in the domain of mathematics, actually not just use given facts that someone provides to them, which is kind of the traditional approach, but also invent new facts that might be interesting or useful. And I will show a little demo of that and explain how we use Haskell's QuickCheck to achieve some of this. But let's start. So we're going to get into our time machine and go back to the 1950s and the birth of AI. So actually solving mathematical problems was kind of one of the earliest tasks that people wanted to solve with these really early AI systems developed already in the mid-50s. So one of the first AI programs was called the Logic Theorist, and it proved theorems about propositional logic from a very famous book, the Principia Mathematica, which was written by Bertrand Russell and Alfred Whitehead, I think it was called. Yeah, Whitehead. Very famous books. They set out on a big project. They wanted to formalize all of mathematics to have really sound foundational truths. And this is a huge book, and it took them several hundred pages before they managed to prove that 1 + 1 = 2, but they were very thorough. Ultimately, it led to a lot of complications and paradoxes, but at least this work was quite influential on what later came to become the field of automated theorem proving. Anyway, this logic theorist was in 1956 published a report by Alan Newell and Herbert Simon, very famous people, Turing Award winners. Simon later also he was an economist, he won the Nobel Prize. And they were very happy with this program that proved some very simple theorems, but nevertheless proved them. They presented it at a very famous conference, the Dartmouth Conference in 1956, which was organized by various influential people like John McCarthy, Marvin Minsky, and so on. And that's where they allegedly came up with the name artificial intelligence for this entire field. And this was presented. So to create this program, this is where we first meet one of our programming languages. They had to invent a programming language. This is like, they barely had computers. It was probably punch cards and so on. But they had to invent a programming language for dealing with list processing, which turned out to later be a predecessor to what became Lisp a little bit later on. Also, when I was looking in this old report, I came across, so remember that I said that I think AI is about reasoning and learning. And this was actually something that, back in the early days, this was a little bit of what they were thinking about. So they write that although the program of LT does not change, so it's not like a neural network, it doesn't update any weights or, well, you didn't have neural networks back then, but it doesn't change the program. But it does accumulate experience in solving problems. Learning does take place in one very important respect. So this program stores new theorems, and these theorems are then available as building blocks for proofs of subsequent theorems. This might sound obvious, but it's not always been obvious in theorem proving. But I think it's very important, and we'll come back to this insight that he had already then. Okay, so 1950s, field of AI is born. What happens next? 1960s, there's a boom of optimisms. Newell and Simon famously say that within 10 years, a digital computer will discover and prove an important new mathematical theorem. So there was a lot of hype at this point. A lot of belief that AI would do all sorts of things. We would have machines translating natural languages. Obviously, recognizing things in images was just around the corner. As we all know, it took a bit longer. However, in the 1960s, there's a couple of very important algorithms that are invented, which are very important for the field of automated theorem proving. And that's the DPLL algorithm for solving programs in Boolean logic, in propositional logic. So that's when the types of your variables are Booleans, so you can basically reason about things that are true or false. And also the resolution algorithm for a slightly richer logic, which is called first-order logic. There you also have, you might have some types and some quantifiers like for all and exist in first-order logic. These algorithms are still used today, obviously various tweaks and improvements and optimizations, but they're still in use today in today's automated theorem proving systems. An interesting little side here, this reasoning in first-order logic and resolution, it actually influenced the design of the Prolog programming languages, which Lars Huppel was giving a talk about earlier today. So there's a connection here again between the development of doing computer mathematics and programming languages influencing each other. So anyway, at this point, we kind of have a theorem proving system which does the following. So they take a bunch of axioms and a conjecture that you want to prove. It feeds it into a black box, which does some sort of reasoning in a search-based manner. So it's a little bit like if you were to play a game like chess and you just enumerate all possible moves you can make. So it's kind of similar to that. You enumerate all possible moves that you can make in the proof to make it go forward, and you use some heuristics to pick the most promising one, some rules of thumb that you programmed into your black box. And it comes out and says yes or no. So these kind of algorithms, they go away a little bit from the vision that they had in the 50s. So first of all, you're kind of proving one thing at a time and you just feed in whatever. So it doesn't accumulate any knowledge. While the human can, of course, put more things in here, but the system itself does not really accumulate new knowledge, to put it simply. And it doesn't generate any proof, so to say. It says, yes, I proved it, or no, I didn't prove it, but it generally doesn't really say why. Okay, so that's where we're at. In the 1970s, there was a famous event. It was called the AI Winter. So in part, that was to do with a little bit of disappointment. So they made very bold claims 10 or 15 years earlier that they were going to solve all these problems. And it turned out, hang on, this is a lot harder than what we thought. And the computers are still not that fast, so it's not really viable to do these big neural networks that we have today. You started having tiny little perceptrons and so on, but nothing like what we had today. There was certainly no discovery of any important new mathematical theorems, no machine translation, no reliable image recognition. In computer mathematics, well, you had these systems that I showed you. You fed in some axioms and facts, but it could be slow. If you gave it too much, then it could be lost. You remember, it was search-based. If there was too many different moves you could make, well, which one should it go down? Basically, it could take a long time. And you got no proofs. So even if it said yes, you don't really know, should I trust this? Should I not trust this? There started coming systems that were called proof checkers. So a proof checker would be able to take a proof which was primarily written by a human and check all the steps. Are these steps correct? But there was little or no automation here. Right. So if we focus again on computer mathematics and theorem proving, there was a little bit of a step back from this thinking of full automation. Well, maybe we can make a compromise. Maybe we can get a little bit of both worlds. So instead of having a fully automated system, people started thinking about having an interactive system that would interact with a human. So here, this is a picture of the lovely city of Edinburgh, which I like a lot. I lived there as a student. And in Edinburgh, in the early 70s, Robin Milner came there as a researcher to develop a system called Edinburgh LCF. So he had previously developed a proof checker at Stanford that was called Stanford LCF. But it was a proof checker. It didn't have very much automation, and it would have been very difficult to build that into the system. So when he came to Edinburgh, he decided to build a new system which would remedy this. And that was Edinburgh LCF. So the idea was that the user, the human user, should be able to program small tactics, they were called. And tactics were little strategies to automate parts of bigger proofs. So at the same time, you also wanted to be able to check proof steps. So the system shouldn't allow any steps that couldn't be checked and were correct. So the system should keep track of all the little nitty-gritty details. And theorems shouldn't be proved in isolation, as in the automated system, not just pull in a bunch of facts and get a yes-no, but actually coming back to this idea that we saw in the logic theorist in the 50s, that you're actually building up a theory and put in, excuse me, and you prove things which you can later use to prove other things and so on. And that way you're building up libraries of mathematics. Okay, and to do this, they needed a powerful language to program these strategies, tactics. And that language was given the name ML, which stands for meta language. So meta language needed to have some very special features. So, for instance, it needed to deal with functions. So these tactics, you want to be able to compose them. So say you want to do a proof by induction. Then maybe one tactic is apply structural induction. And then, well, you get a base case and a step case. So then after you've applied structural induction, then you want to do, say, some rewriting and simplification using other facts that you know on the base case. And then maybe you want to do the same thing on the step case. So you wanted to compose a tactic for induction with one for simplification. So then you needed a higher order language, right? So you need to pass functions around, pass these kind of tactics around, compose them, and so on. So a lot of these features that you see in early functional programming languages was in fact motivated by the need of computer mathematics and interactive theorem proving. Okay. So I'm glossing over. There was also other important development in the 70s, but please come and talk to me later. I like talking about history of theorem provers. Anyway, let's move on to the 80s and 90s. So meta language had a brilliant career also outside of the theorem proving world. It became standardized as standard ML. And standard ML, as you all probably know, had a number of descendants like OCaml, F# that we heard about this morning. It's probably also influenced the development of Haskell to some extent. So this became quite an influential language in the whole development of the functional programming family, I think. And the same thing with this LCF system. So there's actually, I would say most interactive theorem provers today are, in some sense, descendants of this first LCF, Edinburgh LCF systems. So today, you might have heard about Isabel Hall, my personal favorite, Coq. This one is a bit more unusual. This is the logo for a system called Hall, or Hall 4. There's also Hall Light, and so on. So there's a number of these interactive systems. So I think the reason why these were quite successful, and I will show you some success stories in a minute, if we just take a break first, is that they're actually quite a good example of human and computer collaborating. So when you think about AI, yes, computers should do everything. They'll take over the world. Humans will be obsolete. But before that happens, we will probably actually collaborate with intelligent, with AI programs. And I think this is kind of a nice example, because the computer is really good at keeping track of fine details, so small proof steps, going through all the details. They don't get tired, and they don't ever make sloppy mistakes or forget things, anything like that. Humans, on the other hand, we're quite good at the creative part. We can think outside the box. Computers can't really do that. They are the box. We can come up with new theories, new analogies, new conjectures, new definitions, and so on. Computers aren't so good at that point. But that's kind of, the interactive provers kind of hit a nice sweet spot when they were developed. Okay, so, and this actually led to some nice success stories in the 90s. So there was gradually there was an increasing amount of mathematics being formalized in these libraries for these systems. So by 1998, a guy called Jacques Fleuriot, who was then a PhD student in Cambridge, he was formalizing parts of Isaac Newton's Principia, which is to do with mathematical foundations for his work on gravitation and planetary movements and so on. But he actually found a small error when he started putting in this in Isabel and having Isabel checking all the fine details. He did find a small error that no one had discovered for hundreds of years. wasn't a serious one, so I mean, Newton was still right about gravity and all that, but still, he found a small error. Another big example, which is probably my favorite formalized mathematics example, is Kepler's conjecture. So Kepler's conjecture has been was one of the great unsolved problems of mathematics for several hundred years. So it was actually stated in 1611. And it conjectures that the most effective way of stacking spheres, for instance, cannonballs or oranges, is as a pyramid. So the reason Kepler got interested in this was that he was actually corresponding with an English mathematician who was working for some nobleman under Queen Elizabeth I. Queen Elizabeth I was sailing around. She had all these ships, buccaneers, waging wars. And it was very important how you stack the cannonballs in these ships, because he wanted to have as many cannonballs as possible and stacking them efficiently. So it was a very practical problem in 1611. Anyway, it took quite some time before this was solved. And in fact, in 1998, Thomas Hales presented this proof, and it was a big sensation. The proof was 300 pages long and included a computer program of 50,000 lines of code. Okay, why was it so big? Well, it was in fact massive amounts of case splits that needed to be done in these proofs, and each of these cases needed to exclude a potential counterexample. There was many potential counterexamples, so it was like no way of making this proof smaller. It was going to be a huge proof. So Hales submitted his paper in 98, and then he waited. And I don't know how many of you are academics, but sometimes you submit a paper to a journal and you have to wait for quite a long time for the reviews to come back. It can be a bit annoying. Hales had to wait for 4 years. And after 4 years, the referees came back and said, well, we're 99% sure that it's okay, but well, we can't verify all the computer calculations that you did there in your huge big program. 99% is pretty good, but Hales was a mathematician. 99% is not good. It's a proof. He wanted to be 100% certain. So what he did then was that he launched a project called FlySpec. The FlySpec project was basically take an interactive theorem prover, which we were quite certain it's correct, formalize this entire 300-page plus 50,000 line of code proof in a proof assistant, in an interactive theorem prover. They're sometimes called proof assistants, so excuse me if I'm using it interchangeably. And then have this system check each step of the proof, make sure we didn't do any sloppy mistakes like Newton. We want to make 100% certain. So they started this in about 2003. In 2014, they announced that they were finished and that the proof was correct. So this was 11 years later. The final paper had 22 authors and 5 PhD theses had been completed along the way. So this was quite a massive undertaking, but nevertheless, humans and computers collaborating in checking this proof and verifying it was actually correct. Okay. So where are we today? Coming back to this claim that Newell and Simon did in 1958. So not quite there, right? But a digital computer will prove an important new mathematical theorem. That's probably okay. Maybe we can say that. So today we have primarily much faster computers. So yeah, I should say that, well, this Kepler's conjecture, of course, wasn't proved automatically. It was done interactively. So yeah, maybe we've gotten there. But today we also have much, much faster computers than we did in the 60s and 70s. So this kind of algorithms, DPLL and resolution, provers using those algorithms are much, much better today than they were. Of course, the algorithms have been improved in various ways, but we also have much faster computers. So this kind of idea of doing this brute force search in this game that is the proof, looking through all the alternatives, that's not quite as far-fetched and crazy as it was 30 or 40 years ago. So in fact, in 2016, 3 years ago, it was announced that the Boolean Pythagorean triples problem had been solved fully automatically by a SAT solver. So this was an open problem in something called Ramsey theorem for a long time, and it was proved by a computer automatically. Again, the proof was 200 terabytes of propositional logic, so it's not really suitable for human consumption. But again, this was one of these problems which probably doesn't have a proof that's suitable for human consumption. So there are such mathematical theorems that we really need the computers to do for us. So with this result, I think this claim that at least a computer have proved an important mathematical theorem can be said to be true. It didn't discover it itself, but it proved it. Okay, so coming back a little bit to these, so these automated provers have become better. So what impact does that have on these interactive systems that I mentioned before? So of course they try to be the best of both worlds. So they have pretty much embraced this improvements of SAT solver, SMT solvers, if you know what that is, similar but a bit richer theory, and first order provers. So they have embraced it in tools that are often called hammers. So hammer kind of just take the heavy machinery, smash your theorem, do the brute force search, and prove it that way, prove it in a very computer-centric way. So here actually this is about as much machine learning as there's going to be in my talk. So these tools are using some fairly basic machine learning to kind of learn, based on what my conjecture looks like. Remember, these interactive provers, they have a large library of mathematics. So which facts can I pick out that are likely to be relevant for my conjecture? And then I can give it to these brute force systems. I mean, the brute force systems aren't perfect. You can't swamp them with everything you know, then they'll still fall over. But you can learn a little bit, give them a bunch of stuff, and they can prove things for you. So one important aspect is that these interactive systems, we still want them to check each step. So we won't trust some random external system. But we can get some information back from them, yes, this is true, and then we can recreate the proof, which is much easier than doing the search immediately. I will come back to that in a minute. Okay, so we're here today. So what's left of this challenge up here? Well, that's the discovery part, right? And that's something that I'm really interested in. Can we get computers to discover theorems? And I'm now going to talk a little bit about my own work and do a demo. Right, so here's a little functional program. This is written in, if you're wondering, this is written in the Isabelle Hall prover, but for our intents and purposes, it's just some functional program with 3 recursive functions over lists, defining insertion sort, and a predicate up at the top, sorted, which returns true if the list it's given is sorted. So this is my favorite example, because when I was a third-year student and I was doing my first course in functional programming, this was one of the homework assignments at the University of Edinburgh that they like to give bachelor students. So they said, prove that insertion sort produces a sorted list. Okay, so when I was an undergrad, this actually took me quite a while to prove with pen and paper and eraser and going down the wrong ways. I always, when I started working with theorem proving as a PhD student a few years later, this was always what I wanted to get them to do. So now, if you excuse me, I'm going to fiddle a little bit with my screen and bring the demo up. So. Here we go. I hope you can see. So here is the same program as I had up on the slide. Sorted predicate, a function insert, which inserts into a list, and the insertion sort function. Okay. Here's my homework. Now I'm going to cheat. So remember I talked about these fantastic hammers that people use to call these brute force automated prover. I'm doing that right now. I'm going to cheat on my homework. Right. Now this is taking an awful long time. Still, it's probably faster than I would be if I was doing this on pen and paper. But let's see what happens. It's sledgehammering away. Yeah. I'm going to go to the pub instead of doing my homework. Nothing much happening. Timed out. Come on. Right. This is rubbish. I mean, can't 50 years or 60 years of theorem proving, they can't even do my homework. Well, let's call Hipster. So Hipster, we're going to give it sorted. We're going to give it insert and isort. Okay, so now this is going to take about 2-3 minutes. So in the meantime, let me tell you what happens behind the scenes now. So this is the system that we developed at Chalmers. When I type in this command, it's going to call out to an external tool called QuickCheck. Not QuickCheck, QuickCheck. QuickCheck is a Haskell tool for very lazy programmers who can't even be bothered writing their own QuickCheck properties. It generates properties. So what it does is to take these functions that I've given it and start building up little terms out of them. So of course we can't do this naively because then we would get an awful lot of terms. So we'll do this incrementally. We use very clever heuristics and gradually start building up terms, just terms, not equations, but just potential left and right hand sides of equations. Then we use, what do we use next? Well, QuickCheck, of course. So QuickCheck is really good at generating test cases. So we're going to generate a whole lot of test cases for all our bits, potential left and right hand sides, and then we're going to evaluate them. So we have this big pile, we start evaluating them, and then we see what we get. If it's different, then we split them aside, and those terms that keep evaluating to the same things, we keep together. So we get a bunch of equivalence classes after a while. We do a lot of testing. So from each one of these equivalence classes, we then be able to extract some equational conjectures. And the program has actually done that a long time ago. They're coming down here. You can't see them very well now because, but never mind. So these are some conjectures that came out. 15 of them. Some of these okay, so these conjectures are now tested quite thoroughly with QuickCheck, but they're not proved yet. And I actually want to prove them as well. So after we've generated these conjectures, now it's done. I think, no, it's not. We'll bring them back into Isabelle and start doing our proofs. And that's what's taking quite a long time, because now I'm actually throwing a lot of heavy machinery at these conjectures. I'm using induction, I'm using sledgehammer, and so on. There we go, there it was done. So let's see what Hipster outputs, actually. So it's output a lot of stuff. I'm just going to click on this, and it's going to paste in all the theorems and their proofs that it found, like that. And it comes back here, and now the proof of my homework goes through, and it says by simplification adding lemma AC. Let's paste that in. Okay, so great, I didn't have to do my homework. But let's see what it came up with. So let's look at this lemma AC. It's here. Well, that's the same thing, isn't it? So Hipster actually discovered my homework assignment and proved it for me. So let's see how it proved it. Well, it proved it by induction and some simplification and a lemma AA. So one thing that I should say about these fantastic automated provers like Sledgehammer and the provers that Sledgehammer used is that they can't do induction and they can't invent lemmas. So there's two reasons why this didn't go through the first time around. And Hipster has sorted both of those things out for us. So let's look at this lemma AA that we apparently needed to prove the homework. Well, that's what you expect. This is the key lemma that took me a long time to come up with as an undergraduate. It says that if a list Y is sorted, then if I insert some element X into it, it's still sorted. And that's also proved by induction and a bunch of simplifications. Okay, so that's very cool. We can cheat on our homework. I might try and do another very quick demo. So this is all very nice if you're into computer mathematics, but I want to show a different example which is maybe a bit more relevant if you're a programmer. So what happens if I give, so now I'm not going to bother about the proof, I'm just going to do some testing. So what happens if I give Hipster a buggy program? So here is two functions, length and rotate. And I'm going to give Hipster length and rotate. And now I'm not asking it to do really any proofs. So it's just going to run pretty much immediately, come up with a bunch of facts. And these are the ones that were tested by QuickCheck in Haskell quite thoroughly, but not proved yet. So what happens? Did anyone spot the bug in the rotate function? Anyway, never mind. Let's look at the properties that came up. I'm a super lazy programmer. I don't even want to write my QuickCheck properties myself. So we get some properties here. Rotate something in a list with one element. That's okay. Rotating length doesn't change if I rotate something. But this one is kind of weird. So this one says that if I read it from the other way around. So if I rotate around the length of the list, normally I would expect to get the same list. I sort of rotated a lap. I would get the same list back. Here it says that it's the same as rotating the length plus 1. That's just weird. So even though I was so lazy I couldn't be bothered writing a QuickCheck property even, if I at least read this, I get an inkling that something is wrong. So let's... So I've forgotten parentheses. That was my mistake. If I run this again and see what we come up with, then now it's a successor on both sides. I wouldn't want to get that at all. That's the one I was looking for. So I'm not doing any proofs now. So it's still going to have a few superfluous equations in there. But at least it finds this one. If I rotate around the length, then I get back the same list. So now it found the kind of property that I expected to see there. OK. I'm going to go back to the presentation. So where are we now then? So a digital computer has discovered and proved not an important or new, but a mathematical theorem nonetheless. So that's good. We had to scratch out important and new, but hey, it's progress. And how did it work? Just do a little quick. We were here in Isabel. We defined some functions. We defined a little functional program. It got translated to Haskell, to this tool QuickCheck. QuickCheck constructed a bunch of terms, which it tested using QuickCheck. QuickCheck then, based on which terms appeared to be equal, constructed a bunch of equations, conjectures, which we feed back into Isabel. Inside here, we can, in the last example, we can either bypass this or we can do some very easy reasoning and discard some trivial stuff, which is easy to prove. This is a parameter in Hipster, so you can change a little bit what you mean by easy or hard reasoning. Or in the insertion sort example, hard reasoning was induction. So if you manage to prove something, you add it to the theory. Remember, this was one of the nice features of the logic theorists in the 50s. It could use things it had proved in subsequent proofs, and so can Hipster. If it fails, well, it puts it back in this queue, and maybe when it proves something, it will succeed the next time around, and that's what happened. That's also why it took quite a long time in the insertion sort example, because it needed to go around a few times before it had all the lemmas that it needed. OK. So these systems are available to try out. Hipster is available on GitHub. It requires you to have Isabel installed. QuickCheck can be used as a standalone tool in Haskell. Then you get this kind of behavior that I showed at the end. So you get conjectures that are tested quite thoroughly, but they're not proved. But you can use it in for your Haskell programs directly, which is very nice. And I would like to thank all the people who have contributed to QuickCheck and Hipster and made it all such a fun system to work with. Thank you very much.
Okay, I think now is a good time to ask a few questions.
So thanks for that, for a very interesting talk. So if I got you right now, at the moment, those heuristics for generating those small terms and similar tactics are created by you manually. So is there any chance for automating that process, or are you planning to engage some sort of learning in that?
Yeah, so that's actually some of the things that we're looking into right now. Of course, it's a question of gathering data, how we gather data, what data we could have. But I think, I mean, heuristics, they come from someone's experience. In this case, maybe my experience and Nick's experience when we were designing the QuickCheck algorithm. And we must have learned those patterns somewhere. So it should be possible to also train the computer, given that we can get enough data to sort of recognize what does an interesting conjecture look like. So I'm very interested in doing that, but that's future work at this time.
Thanks. Do we have any more questions? Do you think that this human-computer interaction could scale in the foreseeable future to a scale where it's not just for theorem provers, but everyday user programs conversing in a way like you converse with a theorem prover with the user, so you like dialog boxes and you can build your own version of the program you're using, sort of like how dependent type programming works right now with Idris.
So I'm sorry, I'm not very familiar with Idris. I know it's a dependently typed language, but I'm not sure I understand your questions. You're asking if I can get an everyday application to adapt to my interaction to it?
Yeah, and
In
just
what sense?
be much more moldable, so like not a preset of features, but you rather get a program for like Photoshop and stuff like that, and you can build your own version of Photoshop or your own version of, I don't know, programs like that.
Maybe. I mean, why not? I mean, it's yeah. Maybe you can borrow ideas from these theorem provers and putting together features. I don't know if people are working on that, but why not? That sounds like it should absolutely be doable, also in other domains.
Okay. I think that's it. Thank you very much.
Thank you.